Hi, I'm Bill Kuzmal. This is joint work with Stefan Walzer, and the title of this talk is Space Lower Bounds for Dynamic Filters and Value Dynamic Retrieval. So at a high level, what we do in this paper is we revisit two problems having to do with dynamic space-efficient data structures. And in each case, the main result that we prove is a new space lower bound for these problems, showing that actually the kind of dynamic version of these problems intrinsically requires more space than the static version. So that's at a very high level what we do. And for this talk, I'm going to focus most of the talk just on this first problem, not because it's the more important one. It actually, in some sense, is maybe the less important one, but actually just because this first problem will really give me an easy opportunity to demonstrate some of the technical content from the paper. So that's going to be most of the talk. And then at the end, I'll come back and I'll also tell you about the results for the second problem. Okay, so to start, let me tell you about the so-called static retrieval problem. The setup is that you're given a set of key value pairs. So each key is some ki, each value is some vi. And the way to think about this is that the keys represent some set of elements from some universe. Maybe they're social security numbers of people. And the values are b-bit values where we're storing one value for each key. So maybe we're storing the zip code for each person in our data set. And the goal is to build a data structure that supports value retrieval queries. So this means that if we query some key k, and if k is one of the keys in our data set, then the query should return the corresponding value. Now that's the only guarantee. So for example, if we query a key that's not in the data set, well, the query can return whatever it wants. So that's the static retrieval problem. And the main question that you care about is how much space does the data structure have to use? And one kind of surprising and beautiful result from the late 2000s is that you can actually be incredibly space efficient. So you can use space that's very close to just the amount of space that it would take to write down the values v1, v2, v3, etc., without storing anything about the keys. That would take nb bits, and the space that you actually need is just nb plus little o of n bits of space. Okay, so that's the static version of the problem. But for this talk, we're going to be interested in the value dynamic version of the problem. So this is the same setup, except now we want to add a function called changeVal. And what changeVal lets you do is for any key k that's in the data set, you can use changeVal to change the value associated with that key to be some new value. So for example, for a given person in our data set, we could change the zip code that's being stored for that person. Okay, so the result is kind of a semi-dynamic data structure. You can't change the key set. So the set of social security numbers is going to stay the same, but you can change the value associated with any given person. And the question is, with this value dynamism, is it still possible to achieve the same space bound that you got in the static case? And a priori, it might seem like surely the answer should be yes, because in most data structural problems, it's trivial to store the value associated with a key. You just go to some position in memory and overwrite that value. But in this problem, the story seems to be a little more complicated. So even though we know how to get this really good bound for static data structures, for value dynamic ones, the best bound is actually worse. So the best known bound, which is achieved using minimal perfect hash functions, is a bound of the form nb plus n log base 2 of e plus little o of n bits. So this is a bound where we have order n more bits than what we had in the static case. Okay, so of course the big question is, are those order n bits necessary? And what I'm going to focus this talk on is the following lower bound. So what we actually prove is that there is an intrinsic cost to supporting value dynamism, namely the optimal space for your data structure, information theoretically, becomes order n more bits than what it was in the static case. So this actually isn't the only result that we prove for this problem. In the paper, we also give a better upper bound. So we show that you can beat minimal perfect hashing. But critically, the better upper bound is still of the form nb plus order n bits. And what this lower bound shows is that that's necessary. You have to use order n more bits than what you used in the static case. Okay, and what I'm going to do is I'm going to focus most of this talk on just giving you a high-level overview of how we prove this lower bound. And in particular, the proof is actually kind of cute and in some ways conceptually not that hard. And so I should be able to give you a pretty good sense of what's going on within the scope of this talk. Okay, so the high-level structure of the proof, what we're going to do is we're going to assume for contradiction that there is a solution using nb plus little o of n bits while supporting value dynamism. And then under this assumption, what we're going to do is we'll show how to construct an impossibly good compression scheme. So what this means is we'll construct a one-way communication protocol. Alice is going to send Bob some message M. And from that message, Bob is going to recover more than the size of M bits of information. So that's how we're going to get to our contradiction. And in order to construct this compression scheme, we're going to start with the following thought experiment. So imagine that we start with some data structure D1, storing n key value pairs. And suppose that we then use the change var function to change the value for every key in the data set. So for each of the n keys, we change its value from some vi to some different value, v over line I. Now let's call the resulting data structure that we get from that, we'll call it D2. So we perform this experiment, and it turns out the thing we're going to care about is what we call the churn between the data structure D1 and the D2. So the churn is the fraction of keys, not just out of the data set, but actually out of the entire universe of all possible keys. What fraction of them have the property that the value that you would get querying the key in D1 is different from the value you would get querying the key in D2? So the churn is the fraction of keys in the entire universe whose query value changes between the two data structures. And what we're going to do is we're going to make kind of a win-win argument. So we're going to argue if the churn is small, then we can construct an impossibly good compression scheme. But actually, also, if the churn is large, we can also use a different approach to construct an impossibly good compression scheme. So we're going to start with the small churn case. We're going to assume that the churn is little o of 1. And what that means is that most keys in the universe have their values unchanged between D1 and D2. But remember that all of the keys that are actually in our data set, the n keys we actually care about, their values do change between D1 and D2 because We changed them. And so this is where we have an opportunity to achieve impossibly good compression. What we can do is we can encode the key set, K1 through Kn. We can encode it as a subset, not of the entire universe, but as a subset of this much smaller universe, consisting of the keys whose value changed between D1 and D2. And because this much smaller universe is much smaller than our original universe, this is going to create a compression opportunity. So in particular, what's really going on is that if we were given D1 and D2, then we could encode the key set K1 through Kn using fewer bits, information theoretically, than it would normally require. You'll be able to save little omega of n bits of space. Okay, so how can we turn that into a communication protocol? Well, what Alice is going to send Bob is the two data structures, D1 and D2, and then also this compressed encoding of the keys that depends on the two data structures. And then Bob is going to use that to recover the actual key set. And then having recovered the key set, Bob can then query the data structures, D1 and D2, in order to also recover the original values as well as the new values for the keys. So I won't do out the math in detail, but the point is that if you look at everything that Alice sent versus the amount of information that Bob recovered, because Alice was able to save so much space when she encoded the key set, the result is that Bob actually recovers more bits of information than what Alice sends. And so that's how we can get our contradiction in the case where the churn is little o of 1. The other case, of course, is that the churn is at least omega of 1. So what does this mean? This means that at least, say, a 0.1 fraction of the keys in the universe, and again, this is the keys not just in our data set, but in the entire universe, at least, say, a 0.1 fraction of them have their values change between D1 and D2. Okay, so this case is actually the trickier of the two cases. And in order to just simplify things, I'm going to do a little bit of a cheat in this case without doing any defense for why I can do it. So the cheat that I'm going to do is I'm going to go back to our thought experiment, and I'm going to pretend that in this case, we actually did a slightly different thought experiment. In particular, I'm going to pretend that to get from D1 to D2, rather than changing the value for all of the keys, I'm going to imagine that I just changed the value for the first half of the keys, K1 through Kn over 2. So I changed the values for half the keys, and I didn't change the values for the other half. And again, we're going to define the churn of the data structure in the same way. It's the fraction of keys in the entire universe whose value changes. And we're going to analyze, for this modified version of the thought experiment, we're going to show how to get a contradiction in the case where the churn is omega 1. So again, this is cheating because I used one thought experiment for the little o1 churn case and one thought experiment for the omega 1 churn case. But I'm just going to ignore that and explain in this setting how you could get an impossibly good compression algorithm. Okay, so how can we exploit the fact that our churn is omega of 1? Again, in this cheating setting where we're only assuming that we edit half of the values from D1 to D2. Well, now we have a new opportunity for compression. Because the data structures D1 and D2, what it means for them to have omega 1 churn is that they disagree on the values that they return for a constant fraction of the universe. But critically, one thing they do agree on is they agree on the values for the keys whose values we didn't change in our data set. So for the keys kn over 2 plus 1 through kn. And this means that for those keys, there's an opportunity to encode them, to compress them, by representing them not as a subset of the entire universe U, but just as a subset of the constant fraction smaller subuniverse consisting of the keys whose values didn't change. So by representing this half of the keys as a subset of the smaller universe, the takeaway is that if we were given the data structures D1 and D2, we could actually encode this part of the key set, again, the half of the keys whose values we didn't change. We could encode those keys using a number of bits that is omega of n smaller than the normal number of bits that it would take to encode those keys. So that's our compression opportunity. And actually turning this into a one-way communication protocol is a bit trickier than it was before. Because the big bottleneck is that it turns out Alice cannot afford to send to Bob both the data structures D1 and D2. So she can afford to send D1, but she can't afford to also send D2. And this puts us in a tricky position because remember, the way that Alice is encoding this half of the keys is in a way that depends on both D1 and D2. So Bob will only be able to decode these keys if Bob has access to both D1 and D2. And so this is where Bob is actually going to exploit the fact that this is a dynamic data structure. So he can take D1, which was sent to him, as well as the values of the keys whose values need to change, along with their actual values. And Bob can now actually manually perform the edits to D1 that need to be performed in order to get to D2. So even though Alice didn't send him D2, Bob can perform the edits on D1 necessary to construct D2 on his own. So at that point, Bob's going to have both D1 and D2, and that's going to allow for him to recover the actual key set that Alice had compressed. So I won't go through all the details, but the result is that at a high level, Alice is sending Bob a bunch of information, Bob is recovering a bunch of information, but because Alice was able to save order n bits in this one step, the step where she sent the keys kn over 2 plus 1 through kn, because she was able to save these order n bits, the result is that Bob actually recovers order n more bits of information than the size of the message that Alice sent. And so once again, we get an impossibly good compression scheme. Okay, so that was the very high-level overview of the proof approach that we take to get our lower bound for the value dynamic data retrieval problem. And so what I want to do in the rest of the talk is I also want to tell you about the second problem that we study in the paper, the problem of fully dynamic filters. And what's going to be kind of cool is that actually this problem is going to follow a storyline that is both in some ways very similar, but in other ways kind of different from what we saw for the retrieval problem. And once again, our main result's going to be a lower bound, and it's going to turn out that this lower bound actually uses very similar techniques to what we used just a moment ago for the retrieval problem. Okay, so we're going to focus on this second problem. And in order to explain it, let me start by describing the classic static version of the filter problem. So here you're given a set K of n distinct keys, and you're also given a false positive rate parameter, epsilon, between 0 and 1. And the goal is to build a data structure that supports the following type of probabilistic query. So if the query is for a key that is in the data set, the query should simply return yes with probability 1. So there's nothing probabilistic about it. On the other hand, if the query is for a key that is not in the data set, then the guarantee that we want is that there's a pretty good probability that the data structure returns no. It should return no with probability at least 1 minus epsilon. So that's where this false positive rate epsilon parameter comes into play. So those are the types of queries that we want to support. And the basic question you might ask is how much space must such a data structure use? And there's a famous result from the late 70s saying that here you can use a really pretty impressively small amount of space. In fact, the optimal space is of the form n log epsilon inverse plus little o of n. So your space is a function not of the universe size from which the keys were drawn, but just of this false positive rate epsilon. And the space bound is very close to just n log epsilon inverse. Okay, so that's the static version of the problem. But again, what we're interested in is the dynamic version of the problem. And in this case, all that dynamic means is that we want to support insertions and deletions. So an insertion adds a new key that is not currently present, and a deletion removes some key out of those that are currently present. And the user is allowed to do any sequence of insertions and deletions that they want, so long as they're valid, i.e. you're only ever inserting keys that aren't present and deleting those that are, and also so long as the total number of keys never exceeds our capacity constraint, n. So this is the dynamic version of the problem. And unlike the problem that we saw earlier, here what's changing really is the key set. And the question we're interested in is, once again, just a question about space. Can we still achieve n log epsilon inverse plus little o of n bits, like we did in the static setting? And here, once again, there seems to be a cost for dynamism. So there's lots and lots of solutions that are known for this problem, and the best ones that we have use order n more bits than the static solution uses. And so the folklore conjecture is that, once again, there seems to be an intrinsic cost to dynamism, and the optimal space bound, it seems, should be order n bits larger than what you got for the static version of the problem. Okay, so there has been some good progress on this problem. Again, this is the conjecture, and it's actually known that this conjecture holds when epsilon is a constant. Not only that, the conjecture actually also holds even in the insertion-only setting. So no deletions, but insertion only. And the big question has been, does the conjecture also hold when epsilon is subconstant? That's the thing we haven't known. So what we prove for this problem is actually two results. The first is that in the insertion-only setting, there's actually a good reason why the previous lower bound could only handle constant epsilon. And that's because for subconstant epsilon, there actually is a better upper bound. So in this setting, the conjecture fails, and you can get a similar style spacebound to what you got for the static case. Our second result is a lower bound. We show that for the fully dynamic version of the problem, insertions and deletions, actually the conjecture is true. The optimal spacebound really is order n more bits than what you had in the static case. So those are the two results that we prove. I don't have time to go into detail on them. But again, the thing that's kind of cool is that this lower bound, even though it's for a different problem, is actually of a very similar flavor to the one we saw earlier for the retrieval problem. Okay, and then just to wrap up the talk, I want to conclude with a kind of interesting open problem. So it turns out for the upper bounds, the only techniques that we know for getting dynamic solutions actually come very specifically with n log e extra bits of space compared to the static solution. And so there's a real blockage, not just at omega n extra bits, but at this very specific n log e extra bits. In the conjecture, the thing that I think should be true, and the thing that would be really cool if someone could prove it, is I suspect the optimal bound should be of the form n log epsilon inverse plus n log e plus little o of n bits. And if you could prove or disprove that conjecture, that'd be very interesting. Thank you very much.